My name is Jill Tarter, and I'm officially retired, and so my title is Emeritus Director of SETI Research at the SETI Institute. And of course, SETI is an acronym that stands for the Search for Extraterrestrial Intelligence.
Chapter 1: Origins of a Cosmic Detective.
Well, I actually didn't do a whole lot with electronics. I did a lot more hunting and fishing and camping with my dad. And then where all of these pictures in our photo albums from when I was a kid, where I'll be standing there in a beautifully starched little dress with ruffled lace socks and Mary Janes on my feet, holding up a big fish, right? Because these were the tensions in my life growing up. My dad was an outdoorsman, and my mother had been involved in the fashion industry and retail. So she dressed me up, and then I went out and went fishing with my dad. So I had a great childhood though. And maybe, let's see, I think I was about 8 years old. And my dad said, we have to have a talk. Clearly, my mother had talked to him the night before. And so we had this washing machine talk. When my dad and I wanted to talk, he'd set me up on top of a washing machine so that we'd be eye to eye. And he said, your mom thinks that you're getting older and you should be spending more time doing girl things rather than spending time with me. And I just exploded. I mean, you couldn't have said anything that would have made me angrier. I said, that's not fair. Why can't I do both? It's just ridiculous. You shouldn't have to choose one or the other. And, of course, then I started to cry because at 8 years old, I knew if you wanted your dad on your side, right, the tears always help. And so we continued this conversation for a long time. And he finally said, okay, all right, if you're willing to work really hard, then you can do anything you want to do. And I said, okay, I'm going to be an engineer. Now, I don't really think I knew what engineers did, but I knew my dad had a lot of friends, male friends who were engineers, and they seemed to have happy lives. So I said, okay, I'm going to be an engineer. Then, sadly, my dad died a couple of years later. And I learned a really important lesson, which is the carpe diem lesson that most people end up learning a bit later in life. But, I always thought my dad was going to be there. And if I didn't ask him the question today, I could ask him the question tomorrow. Well, it doesn't always work that way. And then I had told my dad I was going to be an engineer, and then I just got stubborn about it. And I said, okay, I'm going to be an engineer. And so I went through 5 years of engineering school at Cornell and got an engineering degree. I got a really good education in problem solving, but it turns out I didn't really like the engineering so much. And in addition, I looked around when I was thinking about graduate school, and I said, if in general engineers are as boring as my professors, I'm going to find some other problems to work on with these great skills that I've acquired. And so then I started taking all kinds of different courses in graduate school and ended up taking a course from Edwin Salpeter on the star formation and the life cycle of stars. And I was just hooked. I thought, that's stars live, die, right? I thought that was amazing to be able to study the life cycle of a star. And so that's what put me into astrophysics. So I all the way along, I just had a lot of fortunate, lucky circumstances. I usually describe myself as the chief cheerleader for all things having to do with searching for life beyond Earth. And we have different ways of doing that. Astrobiologists look for what they call biosignatures, trying to discern some disequilibrium chemistry in the atmospheres of planets orbiting other stars. And in my case, teams that I've worked with look for technosignatures. They look for evidence that someone or something out there has developed a technology and that we might be able to detect that technology even over the vast distances between the stars. And we've been doing this for a while now, and I've been cheerleading all the way, and I don't intend to stop anytime soon. When I was about 8 years old, I was down in the Florida Keys, the west coast of Florida, with my aunt and uncle, who were literally beachcombers. And my dad was there, and he was the center of my universe. And I remember one night walking along the edge of the Gulf, holding my dad's hand and looking up in the sky and seeing these magnificent stars because it was a very dark sight. There were no streetlights back then. And I just had this idea that on some planet around one of those stars, there would be a creature walking along the edge of an ocean with their parent, looking up and seeing our sun as a star in their sky. And I don't know what set of circumstances led me to have that particular worldview, but it's been with me for a long time. And then I did an engineering undergraduate degree and a PhD in astrophysics and was nowhere near SETI until um, a very happy accident happened. My first year in graduate school, UC Berkeley acquired the first real desktop computer that had ever been manufactured, the PDP-8S. And it had no language. You had to program the 11 things that it could do by setting all the ones and zeros. You had to program it in Octal. And I learned to do that. It's kind of a weird skill, but I learned to do that my first year in graduate school. And much, much later, as I was finally getting ready to finish my graduate degree, that piece of equipment, that computer, was obsolete, and it was given to an X-ray astronomer by the name of Stuart Boyer, who had been following NASA's workshops on um, looking for life beyond the Earth. And he said, "Wow, UC Berkeley has a radio astronomy telescope, right? That's up at Hack Creek, and my friend Jack Welch runs that." And so he figured out a way that we could take the data in parallel with the astronomers, and we could analyze it, or that is, Stu could analyze it, looking for signals that were engineered as opposed to astrophysical. That's a great idea, but he had no money, and so he went begging. And someone gave him this old computer, and he said, "What the heck do I do with that?" And somebody said, "Ah, Jill's still here. She used to program that thing." And so he came and recruited me to work on his SETI project, which was called Serendip at Hack Creek Observatory. And I programmed that PDP-8 to be the processing engine for that search. So it was just a delightful accident. And of course, then I went off to do a postdoc at NASA Ames, ran into John Billingham, who was starting up the, what did he call it? The Interstellar Communication Committee at NASA Ames. And I said, "Hey, John, there are more than 40 hours in a week, and I'd like to volunteer with your group and see what you're doing." And so that was it. I've never had any other job except thinking about life beyond Earth. I mean, I never set out to have this as a career path, but I can't think of anything more exciting to work on. And there I was, in the right place with the right set of skills, engineering and astrophysics, and we were off to the races. First of all, being a woman was the first part of it, which meant that at Cornell, as a freshman in the dormitories, I was locked in at 10 o'clock at night, and they didn't open the doors until 6 in the morning, which meant that I was sitting there by myself while all my male colleagues were over in their dorms or in restaurants or bars or something, doing all the problem sets as a group. You take the evens, I'll take the odds kind of thing. But I didn't have that because I was locked in and working on my own. So I got a better education, technically. It didn't do me very well socially, right? I was a bit socially awkward. And then there were all kinds of interesting situations in the classroom. First of all the professors knew me because I was singular. I was sitting there in this sea of male faces. They didn't know most of the male students, at least not early on. So if people wanted an extension on an assignment, they'd send me to go ask for the extension. And that was a little awkward, but I did get to know my professors a little bit better. And, there was the day when I was asked not to come to my nuclear physics class the next day because they were going to discuss the dangers of radiation and male sterility, and they just couldn't do that in my presence. Um, and I want to, what about female sterility? Come on, guys. Um, and oh, things like I think I told Sarah Scholes about first year engineering problems and methods, a required course. Everybody had to take it, a lecture room with 300 people. And I was an only child. My mother was very protective of me as she sent me off to Cornell. And so, just the way she used to do when she sent me off to camp as a younger person, she sewed little name tags, Jill Cornell, into all of my clothes, and in particular onto a label of a sweater that I had thrown over my shoulders. And then I flipped it off over the back of my seat, and suddenly we hear this little ripple of tittering and laughter going back from me towards the back of the auditorium and then down the other side. And finally, the professor stopped his lecture and he said, "What's going on?" And thanks, Mom. The label in the sweater had originally said 100% virgin wool, but my mother put my name tape over the word wool. And so they all then knew that I was 100% virgin. It was one of those moments where you just hope the floor would open up and swallow you whole. But of course it didn't, and you got through it and got some laughs out of it later. It was a little, I got good grades. Because I'm locked in my dorm room working by myself. Um, and so there was a lot of tension because my grades were better than many of my other colleagues or students. And then in my junior year, I made a decision that I was going to get married to the man who had been my lab instructor for my freshman physics class. And he was in graduate school, and we knew that I was going to go to graduate school, and we sat down and we worked out all of our finances, and we said we could do this. We could make this happen. And partially because I was on a full scholarship from Procter and Gamble. Um, one of those is given each year in the engineering school, and one is given in the art school. And I had the engineering scholarship, and it was fantastic. Tuition fees, books, all of that kind of thing. And so we obviously counted on that. But when Procter and Gamble found out that I was planning on getting married at the end of my junior year, they took the scholarship away. They said, "You're not serious. You're not going to be a scientist. We're not going to waste this money on educating you just to go be a housewife and have babies." And wow, that was a devastating blow. So I went to the dean of the engineering college. His name was Dale Corson, and who later became president of Cornell University. And I said, "Dean Corson, this isn't fair. I mean, I've been on dean's list every semester. I'm a good student, and I intend to continue to be a student and a graduate student and a scientist or engineer." And he looked at me and he kindly said, "You're right. It isn't fair. It isn't fair at all." And I have no idea what he said when he called up the folks at Procter and Gamble, but he got my scholarship back for me. It was wonderful, and I thanked him profusely at that point. And then 20 years later, when he was president of Cornell and had an advisory committee to help him decide how to run the Arecibo telescope in Puerto Rico, which sadly we've just lost now. It's collapsed. But back then, I was on that advisory committee. And so I was able to come up to him all those years later and say, "See, President Corson, thank you for believing in me. I didn't just drop out and become a housewife and have kids, you know. I'm on your advisory committee for this fantastic telescope. And I have to thank you once again." And that felt so good. It felt wonderful to be able to tell him that he'd made such a difference in my life. Over my career, I've been able to watch the universe appear to become more biofriendly. We don't know that it is. That's what we're trying to find out. But over my career, we have discovered planets around other stars, exoplanets. When we started, we only knew about 9 in our solar system, and then we demoted one of those. So, but now we know that in the Milky Way galaxy, there are more planets than there are stars. And additionally, we now know about organisms that we call extremophiles, forms of life, not just microscopic, but a lot of them macroscopic, living in environments which, when I was a student, I was taught utterly no chance. That's going to be sterile. No reason to look for life there. But of course, life is there. And it's amazing. So, exoplanets and extremophiles, right? Two big game changers. And now it makes it just seem natural to ask the question, well, with all that potentially habitable real estate out there, is any of it actually inhabited? And so that's just the most natural thing now that we have a different worldview of our cosmos than we did 40 years ago. And so I'm excited. We have a real opportunity in this century to answer that are any of them inhabited question. And so I find that really exciting. It makes me mad to be old because I probably am not going to be around long enough to see the end of that story or the beginning of the next phase of our searching. But young people, graduate students now, are going to have a really exciting way forward in this century. SETI could succeed tomorrow, but the instruments that are needed for finding disequilibrium chemistry in the atmospheres of exoplanets, those are going to take a while to build. And then it's going to take another generation to be big enough to actually do the job. For me, the fun part was getting started with this, right? Helping to, roll this rock up the mountain, right? And so I've had the privilege of being in at the beginning. And because I'm a big frog in a small pond, I've had the opportunity to decide a lot of different things about what we should do. And uh, you don't get out of bed in the morning saying, today I'm going to get a signal today, because you're probably going to go to bed disappointed. But you do get out of bed in the morning saying, today I'm going to figure out how to do this better. We're going to do something that we couldn't do last week. We're going to figure out how we can do it today and then how we can do it better next week. And so that's really satisfying. And I've known all along in this business that I'm probably going to have to train my replacement, because this is not a small task that we're undertaking. This is a really large search, and our tools for doing the search are getting better all the time, and now exponentially faster because computing is improving so rapidly. So, didn't go into this thinking that, well, it'll be it'll be a good thing to do for the first 5 years of my career, and then I'll find something else to do. No, I've pretty much understood from the beginning, and everybody who works on this program understands that we are probably in this for the long haul. And so we try and find ways to reach out to young engineers and students and excite them about the potential of doing this kind of work. It's not everybody's cup of tea, right? People sometimes approach their science as, I'm going to do something, I'm going to publish a paper, I'm going to do something else, I'm going to publish a paper, and I'm going to be successful all along the way. And sometimes they're wise enough to think, and I'll do something wrong and I'll learn from that. But this idea of working on something that might not succeed during your career is a little dicey, and it takes a certain kind of personality to be eager to do that. And then, of course, there's the other shoe, which is that the funding for this activity is anything but stable. And so not only do I have to say, come join us, No, you might not succeed with finding a signal in your career. And hmm, maybe I can't make salary next month, right? So that's another challenge. We'd like to now in my cheerleading role, I'd like to work on establishing an endowment so that this kind of activity, this scientific exploration, can be funded stably into the future because that's what it's probably going to take.
Chapter 2 SETI, the search for extraterrestrial intelligence.
SETI, the acronym, is the search for extraterrestrial intelligence, but that's actually a misnomer. We don't know how to define intelligence. We certainly don't know how to detect it at a distance. What we can perhaps do is find evidence of someone else's technology that is detectable over these vast distances between the stars. So we should actually call it SETT, but SETI's been around for a while and has brand recognition, and we're not changing that anytime soon. But we are looking for evidence of technologies. And there are a couple of things that we've done in the past and new things that we're going to be trying to do in the future. We've been looking for electromagnetic radiation signals, either at radio wavelengths or at optical wavelengths. But we're specifically looking for the kinds of signals that, as far as we know, nature can't produce, but our technologies do it all the time. So, in the radio part of the spectrum, that means that we're looking for frequency compression, for power that shows up at exactly one channel on the radio dial. It isn't spread out over many channels, which is what nature would do, but it's a single channel. And in the optical, we look for time compression. We look for bright pulses that last for a nanosecond or a microsecond. And again, this is something that, as far as we know, nature can't do, but lasers sure can. And so we build instrumentation to put behind radio telescopes or optical telescopes that split the incoming signal, which is voltage as a function of time, split it up into many, many different channels, or we sample the optical telescope very, very, very quickly. So we can detect these compressions in frequency. We can see a signal that shows up at one frequency, and it may over time change its frequency because the Earth is rotating and there's a Doppler shift between the transmitter and the receiver. And because of the rotation, there's also a Doppler drift and the frequency changes. So we write software that's looking for those particular patterns. And likewise, in the optical, we look for bright flashes that show up only at one point and then may not show up again. So you have to be very careful in this kind of work about deciding whether or not what you have detected, what shows up in your data, is actually real, coming from the sky, moving the way the stars move on the sky at what we call sidereal rate, or whether what you're finding in your data is coming from your own equipment, noise that you generate, or that satellites orbiting the Earth generate. And so we have this problem of deciding whether what we've detected is us or them. And over time, that gets to be more and more problematic as there are more satellites orbiting, which not only make the night sky bright with flashes, but make it very loud in the radio because of the transmissions from those satellites. And so we've had to try and get clever over the years. And we certainly spend a good half of our computing resources trying to discriminate between us and them. And I've long thought that the best way to do this is in the radio to use two telescopes that are separated by hundreds of kilometers, sometimes even 1,000 kilometers. And they're both looking at the same place on the sky simultaneously. And then if you find a signal in your primary telescope, you look at the data from the secondary telescope and you look to see if that signal is also found by the other telescope with the appropriate shift in frequency and drift that would be due to the differential Doppler of the Earth's rotation. And then in the optical, because we're looking for single events, a single bright pulse, you also want to use multiple telescopes and you want to use the simultaneity with the light travel time between the telescopes taken into account. You want to use that simultaneous detection as your verification that this is something that's really coming from the sky. So, and now we're on a threshold where we can begin to think about using artificial intelligence to help us with this search. So, in my searches, we have done our signal detection always in near real time, so that as soon as we have something, we can immediately follow up on it. This has turned out to be one of the best discriminants against interference for us. But now, what we want to do is use, instead of saying, is there this particular narrowband pattern in the data? Now we want to use machine intelligence to look at the data in a bias free way and say, not is there this pattern, but is there any pattern? Is there anything other than noise in these data? And that will open up the search to all kinds of different modulation schemes that we have very little sensitivity to at the moment. So by displaying the data as frequency versus time as a two-dimensional image, then we can use all of these wonderful techniques that are being developed for artificial intelligence for image recognition. And I think that's going to open up a lot of new channels for SETI research in the future. Because we're interested in ourselves, we're infinitely interested in humans, right? And we want to know how we stack up against the cosmos. Are we unique? Are we one of many? And if we're one of many, how intelligent are we relative to somebody else, something else out there? You know, in terms of technology, we can't find anybody out there whose technology is less advanced than ours. But it's quite probable that what we do detect will be technology that is significantly more advanced than ours. Most of the stars in our part of the Milky Way galaxy are about 1 billion years older than the sun. So there could be technologies out there that have a large head start. And for me, the real reason to work on this question is to know whether it's possible for us to have a long future. All right. There are so many challenges on this planet today that would indicate that maybe our future is not very long because of mistakes that we have made in terms of living on this planet in a sustainable manner. However, if we detect a signal, then we know it is possible to have a long future, and the reason is statistical, right? We are not going to succeed in this project unless, on average, any technology out there is very long lived. And that's not long in human times, it's long in cosmic time. So a successful detection means that it's possible to have a long future as a technological civilization. And I think that that's really worth going after. I don't expect them to solve our problems, but I do expect, if we succeed, to be inspired by knowing that somebody else made it through this technological adolescence, and we can too. We simply have to find the way. But we know there's an answer. And that's inspiring for me. When we used to ask the question, are we alone in the universe? We used to ask the priests and the philosophers or anybody else we thought was smart. We used to ask them, what should we believe? But that's the wrong verb, right? There is an answer to that question, but what any of us believe isn't going to change the way the universe is. And so the appropriate thing is to do a scientific exploration, to go and try and find out what is. So we've gone from belief to scientific exploration over the past 400, or actually much longer ago, in terms of asking the question. Um, and I think that's the right trajectory. This is an appropriate question to be tackled by scientific exploration in a very systematic fashion. Let's approach that by thinking about something that Stephen Hawking once said. He wasn't eager to have extraterrestrials find us because, using the analogy to Columbus' discovery of the New World, Stephen said it didn't work out very well for the inhabitants when Columbus discovered the New World. Well, for me, I think there might be another answer. Right? First of all, we're talking about them coming here, which means that they have technologies that we haven't yet developed, right? And that means that they're older than we are. And I wonder how you can become an old technological civilization unless you outgrow the bad behavior and the aggressiveness that probably helped you evolve intelligence in the first place. So I'm in the kind of Steven Pinker, um, kinder and gentler, better nature of ourselves school. And I think that cultural evolution, when it begins to take hold, will drive a civilization to a kinder and gentler end. Stephen takes 900 pages to say that that's actually happening here, right? We are kinder and gentler now than we have ever been. And to the extent that we work on this project, SETI, and we talk to your mother or other people out there and tell them what we're doing, I think it actually has to change their perspective a little bit. They have to stop thinking of themselves as just uh, a Californian, an American. They actually, I think SETI holds up a mirror to all the people on the planet and says to them, look, you look in that mirror, you are all the same when compared to someone else out there that evolved on orbiting a different star. And I think that that sameness, that understanding that we are all Earthlings, is incredibly important because these challenges that face the planet, which are undeniable and which we have to find remedies for, these challenges don't respect national boundaries. And we're going to have to find global solutions to them. And so I think if we can shift our perspective to thinking about ourselves as Earthlings, then that has got to be beneficial to finding a way to work together across the planet to come up with solutions to these problems that are very real. So that cosmic perspective is something that I'm eager to talk about, and I think SETI gives me an opportunity to do that. And if you think about the chairman of the astrobiology department at Columbia University, his name is Caleb Scharf. And Caleb has a wonderful way of stating this. He says that on a finite world, that's us, we're on this earth, on a finite world, a cosmic perspective is a necessity and not a luxury. So, to the extent that doing SETI can help us open people's minds, change their perspective. I think it will help us get to a long future. So, the Allen Telescope Array is a collection of 42 6-meter radio telescopes. We had hoped that it would be 350, but there was so much technology that we had to work out in order to build this array as a large number of small dishes for the first time ever that we ran out of money. And 42, well, life, the universe, and everything, that's a pretty good place to stop. And the telescopes are built so that they can simultaneously do radio astronomy and SETI observations. Because the telescopes are small, they look at a large field of view on the sky, big patch of the sky at the same time. And so, in that large patch of sky, there are likely to be objects such as molecular clouds or supernova remnants or pulsars or quasars that radio astronomers would like to study at the same time we're collecting data for SETI. And the question of using radio wavelengths versus optical wavelengths versus infrared wavelengths has a lot to do with how those waves pass through the great distances between the stars. Now, we think of space as being a vacuum, but indeed it's filled with some molecular gas and dust. And when you get to be a wavelength is approximately the size of one of those little pieces of dust grain, then that wavelength is heavily absorbed and scattered. That's why at optical wavelengths, these short wavelengths, like the size of a grain of dust, we've never seen the center of our galaxy in the optical because that radiation gets absorbed, scattered. But when you get to longer wavelengths into the infrared, and then particularly much longer wavelengths in the radio, they essentially don't see the dust at all. So we can see vastly farther through our galaxy in the infrared and in the radio, which is why we think that those wavelengths make sense for someone who is either deliberately trying to create a signal to attract our attention or is using technologies that might very well leak or emit radio or infrared wavelengths. If it's warm, it's going to glow in the infrared. So we just think that this is a good idea. We'd like to look, obviously, what we'd like to do is look at all the sky all the time at all frequencies. If you could do that, that would be the best way to, oh, and with more than one telescope, that would be the best way to find transient signals that last for only a short period of time. But we can't do that yet. We're beginning to be able to do it in the optical. So, yes, our range, how far the signal can go through the interstellar medium, will be more limited. But indeed, the technologies that allow us to actually look at this all the sky all the time have developed there rather than in the radio. But all the sky, all the time, all frequencies, that's a goal. And we'll see where technology takes us. The Hack Creek Radio Observatory, where we've built the Allen Telescope Array, has been run by the University of California at Berkeley since the 1960s. And it's had a series of different types of telescope there. Originally, just a very large 85-foot dish for doing centimeter wavelength observations, and then an array of dishes for working at shorter radio wavelengths in the millimeter. And now the Allen Telescope Array is there. And it's really kind of nice to have your own telescope so that you can look at the sky 24/7. And indeed, in radio wavelengths, you can. The sun is not a bright radio source. So, as opposed to our optical counterparts who have to wait until it's dark, we can observe 24 hours a day. And this has been having that facility and having the really bright folks at UC Berkeley and the SETI Institute be able to develop this new technology, which we could not have done much before we did it, because it takes so much computing to combine all of the outputs of those small telescopes together in real time. Uh, it's been a fantastic opportunity to um, pioneer a new way of building radio telescopes. And now, if you look at the plans for international projects like the Square Kilometer Array, which will be built in South Africa and Western Australia, you can see that those telescopes are all built now as a large number of small dishes. So we actually did something pretty spectacular proving out this technology. My husband, Jack Welch, who's the gentleman who discovered water in the interstellar medium, uh, we had an airplane that we used to fly from our home in Berkeley, California, to Northern California to the Allen Telescope Array up near Mount Lassen. And on one of these flights, we were actually returning to the Bay Area at night, and we're flying along, and we're actually under positive control. We're talking to the ground, and they're following us. And suddenly, at 2 o'clock position, there's this bright light, amazing bright light. And we look at each other and we talk to the ground and we say, "What's at our 2 o'clock position?" And they say, "There's nothing on the radar." And yet we see this thing. And it was the most um, confusing feeling. You say, "Oh, a UFO? Really? Not me. I'm the most skeptical person around, right? How can this be happening?" And it was, oh, it was weird. It was really weird for a good 3 or 4 minutes. We're staring at this. And then suddenly the clouds, which we hadn't appreciated, were there. The clouds broke apart a little more, and we got to see the moon that was shining through a hole in the clouds. So I've had a UFO experience, but it became an explained object fairly quickly. And yet I know this unsettling, confusing feeling when you're seeing something, you don't understand it, you can't explain it, and hopefully you'll be lucky the way we were and come up with an explanation, because certainly didn't have anything to do with extraterrestrials or little green men or flying saucers. It was really confusing looking at something, understanding that I really, because it was dark and there was no reference frame, I couldn't really tell how big it was, how far away it was, but it sure as heck was there. And then I thought, oh, I've been telling people for years to bring me data, to bring me something that I can investigate with respect to their claims of UFOs. Let's get some data. And here I am thinking, well, I can take a picture of that, but that's not going to do very much good because there's no reference. And besides, the ground control is telling me that there's nothing in the sky on their radar at that position. And so it was just, this can't be happening to me. That was my feeling. And how am I going to explain this to someone and tell them what I experienced? But fortunately, we were able to keep watching and come up with an explanation. The moon shining through a hole in the clouds. Over the years, we've certainly had a number of false positives. Most of them we can explain very quickly. But there was a time where I was observing at the National Radio Astronomy Observatory in Green Bank, West Virginia. I think it was in 1998. And our second telescope was in Woodbury, Georgia. And that telescope took a hit by lightning, and that fried a disk drive. And it took FedEx a couple of days to get a new disk drive into this very rural area of Georgia. But we were at NRO. We still had that telescope time. We'd actually rented it back. This was back before we could build our own telescope. And we weren't going to waste it. So we continued observing. And instead of having a second telescope to validate the detection, what we did is we pointed our telescope in West Virginia at a star, and then we'd take data, and then we'd point it off the star and take data, and go back on the star, and then off the star, and then on the star. This is a standard radio astronomy technique called nodding. And an interesting signal would be one that was there whenever we looked at the star, but was absent when we looked in any other direction. And so early one morning, about 5 o'clock in the morning, I started tracking this one target, and lo and behold, there was clearly a signal. Now, we do our signal processing in near real time so that we can, in fact, do the follow-up necessary to try and distinguish between interference. And in our two-dimensional display of the data, with frequency being on the horizontal axis and time being on the vertical axis, what I saw was a series of signals that looked like a picket fence. So multiple signals, and the frequency spacing between each signal was the same from one to the next. Well, that's not Mother Nature. That's pretty clearly an interesting signal. And so I started this nodding. And indeed, every time we moved the telescope, the signal went away and we came back and it was there. And I thought, oh, I had a very clever thought. Although I was very excited and there was a lot of adrenaline going on at this point. Anyway, I thought I'll write a program and I'll ask this program to look at all the data we've collected here at the telescope in the last couple of weeks and see if we've ever seen a signal with that constant frequency spacing coming from some other direction on the sky, not the direction of this star. And I wrote the program and I was so excited. I was pretty sloppy. And so I didn't format the output very well. And when I looked at the output, I missed the fact that indeed we had seen that signal a couple of times before from different directions on the sky. And so now I got really excited. I called the doorman, woke up my colleague, John Dreyer, and he came down and we just stayed on that star all day until it set in the west. And we couldn't figure out right away what it was. But by the time the sun had set, the star had set, we knew that the signal wasn't coming from the star because the rate at which the frequencies were changing was appropriate to a source that was rising up to the zenith, not one that was setting in the west. So we knew that it was something else, and it took us a while to figure out what it was. And it was, in fact, when you have a telescope, it's like the telescope has peripheral vision. It has what we call side lobes. So I can still see my fingers out here, although I'm looking straight ahead. And a radio telescope is like that. And this particular telescope had a side lobe that was very weak, at exactly 90 degrees away from the bore sight, the pointing direction. And what was happening was the SOHO spacecraft, which was orbiting the sun, not the Earth, in orbit around the sun, was getting into that side lobe. And every time we moved the telescope in a different direction, it fell out of that side lobe. I was a little disappointed when we quit tracking that star and went off for dinner. But actually, the worst thing was that we had told our colleagues back in Mountain View what we were doing because we had an identical setup there. And so they could see the data that was being collected. And we went off to dinner, convinced that no, this wasn't really what we had hoped it would be. And I forgot to call the folks in Mountain View and say, sorry, no deal. So they stayed up until 2 o'clock in the morning at California when that source would rise again because they were sure we were going to track it, continue tracking it. And so I had some fences to mend when I got home, right? For not being thoughtful enough to let them know that this was not it. Carl Sagan is not only a good astronomer, but he was a spectacular communicator. And he has the ability to talk to an audience about astronomy, and in particular, his interest in trying to find life beyond Earth. And he was just really compelling. So it's quite appropriate that Lisa Kaltenegger at Cornell University operates something called the Carl Sagan Center for the study of life in the universe. Well, Carl wrote, along with Joseph Shklovsky of the Soviet Union, the first real book about modern SETI. It was called Intelligent Life in the Universe, I think. And that book really did energize lots of students and scientists and engineers about the possibility of actually conducting a search. And it was the first time that at a popular level, there had been a scientific discussion of this idea. So he is early into this game of thinking about life beyond Earth. And he communicated the excitement of that idea and the fact that indeed in the 20th century, we actually had some tools to be able to launch a systematic scientific exploration to try and answer this question. So he was very, very influential. And of course, Cosmos talked to the majesty of the universe and really resonated with the public. Carl was an absolutely brilliant communicator, and we miss him. Absolutely. Uh, there have been others that have come after him, but no one individual that still has the impact that he had. He would go out and lecture at a university, and he would have students come up to him and say, Cosmos, that's what made me a scientist. That's what inspired me to become a scientist. I get a little of that today because of Contact, which is now over 20 years old. And particularly young women will come up and say, Contact, that was my favorite movie. And it inspired me to become a scientist. So it's gratifying, but I sure miss Carl. I was back visiting Cornell for some symposium, and Carl said, come on up to the house tonight. We're having a cocktail party. And so I did. That was always fun. And when I got there, Anne Druyan, Carl's wife, and Carl took me off to the corner. And Anne said, Carl's writing a science fiction book. And I said, yeah, I know. The New York Times told us last weekend what kind of an advance he got for this. And we're all jealous as hell, right? And Annie chuckled and she said, well, she said, I think you might recognize one of the characters, but I think you're going to like her. And so I said, oh, come on, Anne. Look, just make sure that Carl doesn't have this female character eat ice cream cones for lunch. And then nobody's going to think it's me, right? Nobody will be confused. And that story is because we were over at NASA Ames Research Center and there was no good food, but we could walk at lunchtime over to a Baskins and Robbins and get ice cream for lunch. And that I got teased a lot about that over the years. But indeed, Carl sent me a pre-publication copy of the book, Contact, and I was going, wait, Carl doesn't know this about me. How did he? How? And it turns out that when I was a fresh PhD, I got invited to a meeting in Washington, and I walked into a room of 80 female PhDs in all kinds of STEM fields. life-changing experience for me. I had never walked into a room full of women. Very comfortable walking into a room full of men as the only woman, but never a room full of women who were so smart and bright. Um, and we did a little bit of uh, amateur demographics, and it turned out that many of those women had their fathers die when they were young, just like me. Um, Many of those women were competitive, and this was pre-Title IX, so there were no women's sports teams that you could try out for. The only thing you could try out and compete at was baton twirling or cheerleading. And so an overwhelming number of the women had been drum majorettes or cheerleaders in their high school years. I was a drum majorette. Uh, the the T-Bird, which is a 54 T-Bird, was America's first real sports car. Now, I was in love with that, and the character is as well in Contact. It turns out that I told Carl about this meeting, and we'd written a little report, and I sent him the report. And I'm just very prototypical of all those women. And so Carl got many of these anecdotes or traits or characteristics out of that report I sent him. And because I'm so prototypical, I even thought it was me. I'm often introduced as being the woman who was the inspiration for Ellie Arroway, played by Jodie Foster in the movie Contact. And I am in a little way, but really that character is an amalgamation of traits of female scientists that Carl had worked with. And actually, I think the character is Carl himself, right? I think there's a lot of Carl in that character. And anyway, it was fun to be able to work on a set with Jodie Foster. She's very, very brilliant. She's also very kind, and that was a great privilege to work with her. She told us that she was never going to teach anyone any science, but she was interested in the character of scientists. Were we passionate? Were we supercilious? Do we have big egos? All this kind of thing. And I think she did a grand job with that character. I'm sure that there's something that we haven't quite thought of yet. I'm sure there's physics and technology that we haven't yet understood or invented. So I can imagine that in the future, there will be other technologies that may make sense in terms of trying to find life beyond Earth. Certainly, we can look forward to these new astronomical instruments, very, very large telescopes, ground-based and in orbit. We're now in the era of 10-meter telescopes. We're going into the era of 30-meter telescopes. And we can think and scratch our heads about when these telescopes make images of other planetary systems. What might they see that would be an indication of someone else's technology? Not just astrophysics, but actually what kinds of technology might these large optical and infrared telescopes be able to discover accidentally, serendipitously? Right? I like to point out that there's this wonderful star system called TRAPPIST-1. It's a tiny little red dwarf star, much fainter and smaller than our sun. But it has in orbit around it 7 Earth-size planets. And so one Sunday above the fold in the New York Times, there's this beautiful artist conception of these 7 worlds orbiting these tiny red star. And an artist had colored them all different. And they should all be different, at least in terms of their temperature, because they're at different distances away from their star. But what if we finally get the ability to image those 7 worlds. And we find out that 2 or 3 or 4 of them are all the same when they shouldn't be. But perhaps some advanced technology has geoengineered these planets to turn it into the type of real estate that they particularly prefer. So I look forward to that kind of exciting, potentially serendipitous detection. Um, and in the radio, we're building uh, bigger telescopes, like the Square Kilometer Array, which will have more sensitivity and be sensitive to fainter transmitters. And then in the optical and the infrared, we're building these telescopes that can look at huge areas on the sky, something called SETI, something called laser SETI. And this is our first opportunity to try and go towards that all the sky, all the time coverage that will make us sensitive to transient signals. So I'm really excited, and eventually we may build the Square Kilometer Array in South Africa. We may build the next generation of VLA telescope across the southwest of the United States, and we may orbit large um, optical telescopes, infrared telescopes that will allow us to do these studies of the atmospheres of distant exoplanets. And so I think that the future is really using astronomical instruments. We're talking about the future where some of these instruments actually might be usable for SETI in a commensal way, not dedicated to SETI, but we can use the data that they collect perhaps to do some SETI explorations. So I'm excited. And of course, as I said, maybe what we should be looking for are zeta rays, right? Not radio or optical or infrared, but zeta rays. Now, I don't know what a zeta ray is because we haven't invented it yet. But if we do in the future, and if it makes sense, then we should start looking for other technologies using zeta rays. In my opinion, and it's only an opinion, I think we're too young to start broadcasting. Broadcasting is a difficult and more expensive job, and it does no good to broadcast for 15 minutes, for 2 years, for 5 years, right? Because your signal is going to go past your intended recipient in a few minutes, in a few years, in 5 years, right? You need, if you're going to broadcast, you need to start and not stop so that when another emerging technology out there begins to explore its universe with tools that are appropriate to detect your signal, the signal will be there for them to find. So I think we need to grow up first. We need to become an old, stable, technological civilization. And then we should take on this hard job of broadcasting and do it forever.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.